So what I'm going to do is talk a little bit about machine learning and solutions we've developed using machine learning technology within Amazon. This is going to be a little bit of have a flavor of a tutorial, sort of tell people about what machine learning really is and how it's used, and what we do with it in Amazon. How many people have heard about machine learning? Okay, quite a lot of people. How many people have used machine learning in their jobs? Okay, very few. How many people have taken Andrewing's course on machine learning online? Okay, just a few. Okay. Well, there's some good online resources for people who are interested in machine learning. Hopefully this will just give you a sort of an initial introduction and pique your curiosity enough that you go in and look up other resources on the web. We are also going to have some shopping carts that we are giving out. These are real pretty I think you can fit in some stuff in there, maybe chocolates or something. So people who sort of answer questions or ask some really interesting questions, we'll be giving out these shopping carts to the audience. So let's keep this session very interactive. If you have questions, raise your hand, and clearly if you have a really good question, you'll get a shopping cart. So here's just the overview of my talk. I'm going to start off with just describing what machine learning is and why it's important. I'll talk a little bit about some of the key concepts in machine learning and problems like classification, regression, overfitting, underfitting, regularization, bias variance, and so on. Some of it gets a little mathematical. I'll try to explain it in as simple terms as possible. Then I'll go on to talk about some of the applications we have at Amazon. Machine learning these days is a machine learning solution. So let's look at what machine learning is. At a very high level, machine learning systems discover hidden patterns within the data, and then they leverage those patterns to make predictions about future data. Okay? So you discover hidden patterns in the data, and then you use those patterns to make predictions. That's machine learning in a nutshell. So what's an example of a pattern, right? I mean, one example is, say, if a product title, within the Amazon context, if a product title contains the keywords jeans or jacket, then the product belongs to the apparel category. Okay, so this is sort of a classification problem. We are looking to put products in different categories. And a pattern could be, well, every time you see jeans or jacket mentioned in the product title, the product actually should be classified into apparel. Okay, so that's a pattern, okay, between keywords and categories, right? And machine learning systems learn from examples. Okay, this is not very different from how humans learn, right? You look at children; they learn a language just looking at examples. Kids don't, 5 or 6 year old kid really doesn't know rules of grammar, right? But they still speak grammatically correct English. And that happens because they learn from examples. They see adults speaking, and that's how they learn, and they start speaking as well. Okay. So those are the two things to keep in mind. One is you discover patterns in the data automatically, use them to make predictions, and the other thing to keep in mind is you learn from examples. So machine learning systems have to be given examples, and they learn from examples. Okay. So why is machine learning so important, right? Why not just write a program for everything, and that should take care of really just write code to solve all your problems. That typically works in most cases, but there are many problems like handwriting recognition or speech recognition or detecting objects and images. Many of these problems that humans are very good at, right? Computer vision, speech, reading books or reading handwriting. These are very difficult to solve algorithmically. They're not amenable to algorithmic or rule-based solutions, right? I mean, try writing a program to recognize the digit 8, right, or 9, or 7, right? I mean, it's not easy to write a program that will recognize digits, right? But these class of problems, they're very easily solved by machine learning approaches that try and recognize patterns in the data. So you give lots of examples of handwritten sevens or handwritten digits, and the machine learning algorithm actually learns to recognize patterns, right? That's where a lot of times people refer to machine learning even as pattern recognition. So, there are lots of these problems that really are very difficult to solve algorithmically, right? I mean, you can't write a program, so machine learning approaches are typically much better at these sort of problems. And many times, especially in the more recent years, we require to solve these problems at scale, right? These patterns need to be recognized repeatedly at scale, right? If you look at Google, they need to perform searches, detect, rank images. There are billions of, pages on the web and so on. So we have 1 billion products in our catalog. So when you have to do these things at scale, then humans are no longer a viable option. You can't use humans to sort of look at images and figure out whether there's a horse in the image. Suppose you were looking for all images containing a horse, right? It won't scale. I mean, you can't have humans, you can't have an army of humans looking at 1 billion images trying to figure out what objects there are in the images. So you need to rely on automation, and automating these using machine learning is the only option. And in many cases, these patterns change dynamically in time. They're embedded in large amounts of data. Like I said, you can have billions of web pages, billions of images. So the scale is very large, and in these cases, machine learning is the only way to solve the problems, right? And of course, I mean, one has to be careful here. Machine learning is not a panacea of every problem out there. There are many problems where machine learning is not required. For example, if you just want to look up the phone number or the address of a customer, or retrieve, the ISBN number for a book, you don't really need machine learning for these problems, right? So there are a specific class of problems where you want to look at machine learning. Okay, so there are many machine learning methods out there. I'm going to focus on one type of one specific machine learning method in my talk, which is called supervised learning, and this occurs very frequently in practice. How many people have heard about supervised learning? Okay, can you tell me what is supervised learning? Whoever answers that question can we'll give out a card. Yeah. Now, what is the difference between supervised learning and unsupervised learning? Yeah. You provide a training set, but what's the difference between supervised and unsupervised learning? The data is labeled, exactly. Okay, so he gets a shopping cart. Yeah, that's exactly the difference. I mean, supervised learning, we have training data that's labeled. Okay, so let's look at what supervised learning looks like. So in supervised learning, there are two distinct phases. There is a training phase and there is a prediction phase. Okay, so in the training phase, you're given training examples, xi, yi. So there are many such pairs, xi, yi pairs. Each xi is a feature vector. Okay, and I'll explain what features are in just a bit, but just keep in mind that this is sort of a vector of feature values, okay, the xi's. And yi's is the target variable, okay. So it's some target variable. It could be, 1 or 0, true or false, so you have some target variable. And what the machine learning algorithm tries to do here is it tries to learn a function f that best fits the training data, right? And by best fits the training data, what I mean is yi is approximately equal to fxi for all I. Okay, so for all your examples that you have, let's see. Okay, this does work. Okay, so for all the examples that you have, x1, y1, x2, y2, all your pairs that you have, you're going to learn a function f, okay, such that when I apply the function f to xi, I get something that's very close to yi, okay? So it can be exact. You may not, there may not be an exact relationship because there's always noise in the data, but you try to get yi as close to, you try to learn f so that fxi is as close to yi as possible. And this function f is what we call models in machine learning. Okay, so the function f that the algorithm learns, that's the output of the machine learning algorithm, is this function f. Okay, and now in the prediction phase, what happens is you're given examples that you've never, you're not seen before, and you don't know what the y is. So you don't know what the target label is, okay, for the example. And what we're going to do is we're going to use the model f that we learned to predict y. So we're going to predict y using fx. Okay, so we're going to take the x, we don't know the y, so we're going to take fx, and we're going to use that to predict y. Okay. Does that make sense? Have people understood that? So here's just an example of how that works. So here you have in the figure you have a website, right? And the features are things like URL, the words in the web page, hyperlinks, right, that go in and out of the web page. And all these are these features, they're also called attributes many times. All these features are fed into your model, and your model makes a prediction. Okay, is this site an e-commerce site or not? Okay, so we use this in Amazon. As a matter of fact, we use it to sort of classify web pages that are e-commerce pages versus non-e-commerce pages. So this is called a binary classification problem. Okay, so again. This is a very this slide just summarize gives you a complete overview of supervised learning. So if you understand the slide, you pretty much have understood the basics of machine learning. Okay, so there's a training phase. You learn. Yeah, go ahead. Okay. Yeah, that's a great question. I think we can give out a shopping cart for that one. How many examples do I need, right? It really depends on the problem that you're trying to solve. It's not uncommon to have millions of examples, 50 million, 100 million examples for some applications. Where you have text and so on, but there you can also train models with as few as 10,000 or 20,000 examples. Clearly, having the more examples that you have, the better your models are going to be. Of course, beyond a certain point, adding more examples don't help, but you can never give the algorithm too much data. So as many examples as you can potentially get is good. But clearly many domains, it's very difficult to get lots of training data. I mean, for advertising, you can get millions of examples because it's clicks or not clicks, they're all automatically generated. But if you are generating training data by having humans sort of label images, for example, you're trying to build a model, let's say, to detect whether an image has a horse or not, right? So you need humans to actually label it. Yeah. Okay, a question, yeah. How are the harvested? That is really dependent on the system. I mean, it depends on your application. Typically, you have to instrument your system. So, for example, in advertising, you will instrument your ad servers to actually collect which ad was shown, whether the user clicked or not, and so on. So that, and the target label there is click or no click, right? So that's the thing, yeah. Okay, 2 questions there. Maybe you can ask your question. Yeah, go ahead. The feature vector actually is multiple feature values. So it's already multiple values, and the target vector, value is the single value. Yeah. Yeah, yeah. You can have many different. You can have many different features. It's a vector. Yeah, yeah. Go ahead. Yeah. Last question, and then I'll move on. Go ahead.
How can you stop your machine from becoming a turkey? So you've heard of the turkey problem, right?
The turkey problem? No, I've never heard of that.
Okay, so there's this turkey. So when it grows up, I mean, every day the farmer feeds the turkey, and the turkey thinks the farmer is a great guy. And every day when he's giving statistical confidence that the farmer is a great guy, until Thanksgiving. When he has the highest statistical confidence value, this is the greatest guy I've ever met, because he feeds me every day. That's the last day. He's highly confident.
Right. Yeah. So that points to poor training data. I mean, if the turkey is only seeing the good side of the farmer feeding the turkey, and not seeing the bad side of the farmer killing other turkeys, then that's poor training data. If the so you got to make sure you've got good quality training data, so that you show all sort of aspects of the problem. So your training data has to be very balanced. And
I'm talking more about black swan. Can the machine learning predict?
Yeah, it's not going to be look, again, this is not magic here. Okay, it's very simple. You have to show similar examples, and it's going to be able to extrapolate. Machine learning algorithms, the way they work is, when you give it an unknown situation, they will try to match that unknown situation to previous situations they've seen, the algorithm has seen, and based on this matching, so it'll try to say, well, okay, look at this situation. It looks very similar to some previous situation that I had in my training data, and here are 3 situations that were very similar, and it's going to use what happened in those situations to try and predict, right? So if you give a situation that's very dissimilar to anything else in the training data that the algorithm has seen earlier, it's not going to be able to make a good prediction. It's as simple as that. So your training data, so it's not magic. It's very, in a nutshell, it's very simple. You're just looking at, so when I give attributes, like here's a male of 30 years of age, living here in Bangalore, blah, 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 who bought this. When I come up with a new person, I'm going to try and find similar people to that person and see what they bought, and based on that, I'm going to make predictions on what's the most likely thing this person is going to buy. So it's just a simple, it's simple trying to find very similar or matching points, examples or people, right, and then make the prediction. Okay, so let me move on here. Again, there are 2 types of supervised learning problems: classification and regression. Classification, your target value y is categorical. That means it takes discrete values. So examples of classification problems are the problem that we just saw, classifying web pages as e-commerce or not e-commerce, or classifying products into many different categories. Now, depending on the number of target labels, this can be either a binary classification problem, if you have just 2 labels, target values, or you have many target values, in which case it's a multi-class classification problem. And there's a whole lot of classification models out there: logistic regression, decision trees, random forests, support vector machines, and so on. And then there are regression problems where your y, your target variable y that you're trying to predict, is a numeric value. It takes continuous values. So for example, if you're trying to predict the price or the demand for a product, then it is a regression problem, and there's a whole lot of different problems out there that are linear regression, and there's many different problems out there. Okay, so let me ask a question here. Let's say I'm trying to detect email spam. What would be good features that you would use, and what's the target variable? Keywords, okay, you can give a shopping cart to him. That was good. So the keywords in your email would be good features to use to try and figure out spam, because clearly, I mean, we know what typically spam emails, a big chunk of them was sender. Okay, that's not bad. We can give you.
If it is having some junk from, no, you'll identify.
Okay, if it's coming from Nigeria or something.
Yeah, region-wise we can do it.
Okay, so that's fine. We can give him one more card. We're running out of cards here. Okay, so the bar has become higher now for giving cards. Lot of numbers? Oh, number of recipients. I see. Okay. Okay, embedded links. Huh? Object? Something repeating. Subject. Oh, the subject, you're seeing a lot of, well, then you've got to be Yahoo or something where you see a lot of mails coming in with the same subject. Okay. Okay, okay. So I think those are good suggestions on features, although I think the sender and the keywords are probably the best indicators of spam, certain IP addresses. User classification. Okay, okay. What would be the target variable that you're trying to... Spam and not spam. You can give her one. Okay, that was an easier one, but okay. Well, you guys have picked up a lot very quickly. Again, this is a little bit of a technical slide, and I'll just go over it very quickly. But you know, we saw that when I said in the training phase, what we're trying to do is learn models that really fit the training data, right? And what we're doing is, you know, trying to find this function f. These machine learning algorithms that work actually they solve an optimization problem. They try to find the f so that they minimize the loss function. And the loss function intuitively captures the difference between the actual target value and the value predicted by the model, right? I mean, earlier we saw that we wanted yi to be as close to fxi, right? So what the machine learning algorithm tries to do is it tries to minimize the difference and between yi and fxi for over all the examples. And there are many different types of loss functions. So you're trying to find an f so that you minimize the sum of loss functions, right? And then clearly the most intuitive loss function you could use is just the simple difference between yi and fi. So typically you just take the square of y and the difference between yi and fxi. You also have other loss functions like logistic loss and hinge loss. The first one is called squared loss, and that gives you linear regression models. For classification problems, people typically use a logistic loss function. That gives you logistic regression models. And then you have support vector machines and so on, and they use hinge loss. So there's different types of loss functions that one can use. Now, very popular models out there that really scale, I mean, at Amazon and Google and Facebook, and all these companies that have extremely large data. So for example, if I were doing spam detection for emails, I would use linear models. These scale to very large data sets. Okay? There are many other modeling techniques where the scalability is different. I mean, solving the optimization problem is very challenging, right? So what linear models do is they make the prediction, they assign a weight to every feature, okay? So the machine learning algorithm learns a weight for every feature, and then the prediction is based on the dot product of the weight vector and the feature vector, right? So it just takes the weighted sum of all the features, right? And every feature has a weight. So here, w.x is actually the dot product of the weight vector and the feature vector, which basically says take the weight for every feature, take the value of every feature, you multiply the weight and the feature for every feature value for every feature, and then you sum it up, right? So here you can see it's like 5 times age plus 0.003 times income. Now age and income are both features, and the weights are 5 and 0.003, right? And in the training phase, you're learning the weights, In the prediction phase, typically the way you do it, when you've got a regression problem, you're just trying to predict a value, numeric value, you just use the score that the classifier returns, the model returns. Otherwise, you take the score, and you typically, for classification problems where you're looking for something like spam and not spam, or e-commerce and not e-commerce, you take the score, W times X, and you compare it with the threshold. If it's larger than the threshold, then it's spam, and if it's less than the threshold, it's not spam. So typically, you'll take the continuous values that the models return, and you'll compare them with the threshold, and then make a call. Yeah. Yeah. What's that? I didn't quite get it. Oh yeah, there's always going to be suspicious cases. So you're not going to get every prediction right. How do you? Yeah, so there are ways of selecting the threshold. So typically when you have predictions, you say, well, I want so much precision. So I'm willing to make only so many mistakes. So I want to be accurate 1 out of 10 times. I want to be correct, right? So then that, when you set that requirement, then the threshold will be set. If you say 1 out of 100 times I want to be correct, then the threshold can be lower, right? So the threshold value is determined based on how much accuracy you want. Okay. Yeah.
Can the system be made adaptive? As in, okay, fine, I kind of recognize the pattern. The user actually said, this is what I was not really looking for. Then you wanted to redirect it to my spam folder, for example. Now, I have learned that as an example.
Yeah, of course. So the user says, well, you misclassified this as spam, it wasn't spam, then that can be taken in as a training example and fed back. So whatever inputs you get, feedback you get, you take that and you use that to augment your training set, and then you retrain the examples. Yeah.
Are you changing functions always? Self-learning, right? Once you define a model.
Yeah. No, the weights can keep changing. Every time you retrain the model, the weights can change, but the form of the function stays the same. Yeah. No, the function here is nothing but the weights. In a linear model, the function is the weights. Okay. So those are learned in the training phase. Okay. Sometimes you have online algorithms where the weights can keep getting updated. But in the training phase, the weights get learned for a linear model. Okay, I'll take one last question.
Every time like a pattern match, for me, it's looking like a pattern match than a prediction is something that's going to happen, you tell now. But this is more like you find the best match in what you actually have. Why is it called prediction?
Well, prediction, all of us make predictions, right? We predict, a lot of us are predicting who's going to win the election. It's based on talking to people, so everybody makes predictions based on data that you have seen, right? So here, you look at the training data that you have, and you see what happened in the past, and based on that, you make a prediction, right?
I find
the task of making predictions is very intricately related to pattern matching. I mean, that's how we make. That's how our brain works. We have patterns in our brain, and we match any situation to the patterns that we have in our head, whichever the closest. We look at what the outcome was for those closest matches, and then we make predictions based on that. Okay. Yeah. Right. Yes. The machine learning models can also tell you the confidence they have in a prediction that they make. So that's also the nice part. It's not like you're just getting a prediction. You're also getting, I'm making this prediction, I'm 98% sure that this prediction is accurate, or I'm only 10% sure that this prediction is accurate. So clearly when you get very low confidence values in the predictions, then you don't want to ignore them. So, and what it means is the model has not seen enough training data of this sort. So you've got to give it more training data of that sort.
Correct. So how do you understand, like, what are the training data to be collected at this point of time?
Well, again, I mean, if you're getting very poor confidence in a lot of predictions, then you've got to collect more training data of those types. I mean, that's how you go about adding your training data.
So the confidence level is getting calculated some ways?
Yes, the machine learning models even return a confidence value.
Okay, thank you.
Yeah, let me just move on here. I just want to explain one or two more concepts in machine learning, and then I'll just talk a little bit. We'll be running out of time within 15 minutes, so I want to spend some time talking about what we are doing at Amazon with machine learning. So overfitting. So again, one of the things to keep in mind as the goal of machine learning is to really learn models that can generalize beyond the training set. It's not, the goal is not really accurately predicting on the training examples. The goal is to predict really well on unseen examples, future examples that you have not seen before, right? So, we use the training data though to learn the models, right? So if you're not very careful, what you're going to end up are models that overfit the training data. So they may be very accurate on the training set, but they predict very poorly on unseen examples, right? And this slide here explains overfitting, right? So if you look at it, those black dots are your training data, right? And you can see a pattern. There's a pattern of, as X increases, Y also increases. It's about linear, okay? The pattern of increase is roughly linear if you look at it the way Y is increasing with X, right? But if I look at this model, it's a very high order polynomial function. So it passes through all the points. So it fits the training data exactly, right? But clearly, I mean, if I take some training point, some X coordinate, which is sort of not in the training set, it will make a prediction which is down there. But we know that, this is a linearly increasing sort of trend. So it should have kind of got something on the linear, on that line there. That would be as close to the line as you get, the better you are, right? So the basic idea here is one has to be careful when you're building models, is you're not trying to really fit the training data. You're actually trying to learn models that can predict well on test data, right? On data that you've not seen before, right? So that's an important thing to keep in mind. Another problem is underfitting. And in underfitting, what happens is your model really doesn't have the expressive power to capture the target data distribution. So if you look at this example here, your target value Y is actually nonlinear in the feature value X. So you can see it's linear for some part and then it goes down, right? It could be, age versus salary, right? I mean, as you grow, as you become older, your salary keeps going up, but at some point your salary starts, either becomes stable or starts going down. So, the problem here is that if you just use a linear model, right? So you're only using a line to model what Y would be as a function of X, you're never going to capture it very accurately. So your model doesn't have the expressive power, right? So I'm just going to skip some of this. So I think the point there was to keep in mind that, there's overfitting and underfitting are two big problems in machine learning, and there are ways of dealing with it, of increasing the power, expressive power of your models with more features and so on, and also making sure that your models are very generalizable. So let me just quickly talk a little bit about Amazon. So at Amazon we have two real core businesses. One is our retail business, which involves really selling products to end users, and we offer a lot of different different websites, different products, different programs. And then we have our seller business, right, where we have our marketplace where third-party sellers can be selling their products, right, and users buy that. But any third-party seller can be on the marketplace. And there's a whole bunch of different websites. We're selling shoes, apparel, and we have a Groupon style business. We're selling groceries. We have a program called Prime, where we give free 2-day shipping in the U.S. to all sorts of customers. The reason I'm talking about these different programs is at Amazon we use machine learning, for example, just as an example, target people, like find out which people have a high propensity to maybe subscribe to Prime, right? I mean, this costs about $100, but you get free shipping. So clearly, customers who are buying a lot of products, incur a lot of shipping charges, are good candidates to actually subscribe to Prime. But there are lots of other patterns we find in the data, right? So what's the exact price of Prime right now? Does anybody know in the US? Huh? 79, okay. Who said 99? Okay, you can give them a shopping cart. Yeah, we just increased the price to $99, okay. We also have visual search. So here's again a place where we use machine learning. You can take a photograph of a product, and then we search in our database of images, product images, which are the products that are very similar to the product that you've clicked, and return those products. So we also have similarity search for products. And of course, I mean, we have our marketplace. We offer a whole lot of services to sellers, where we will store their products, ship their products. We will also handle all the payment information in terms of credit card payments, disbursement to sellers, and so on. So a lot of different products for sellers as well. Within Amazon, we have a host of areas where we are applying machine learning. So just on the retail side, I talked about demand forecasting. So you're trying to forecast the demand for a product based on historical data. This is very important because we need to know as an e-commerce, e-commerce business, how much of a product, of each product we should be ordering, right? And it's a function of demand. And this is not only demand or cumulative demand. We have many different warehouses across the world. So each warehouse, how much product should we have, right? Also, we deal with lots of vendors, so even predicting how much time it's going to take a vendor to ship the product to us. Believe it or not, depending on the time of the year, depending on the product, the times can vary a lot. So you literally have to use prediction, again, machine learning to kind of try and get, how much time a product's going to take to reach the warehouse from the vendor. We also use machine learning for product pricing, so trying to determine what's the best price for a product. We use machine learning out there. There's also, product search is again another place where machine learning gets used. So you're given keywords, right? People type in search keywords. We're trying to figure out what are the most relevant products that match those keywords. Of course, when you rank, you look at the products, how popular they are, how do the keywords appear in the title of the product, do they appear in the description of the product, and so on. Product ads is another area where we use machine learning. Here you're trying to predict the probability of a click for an ad. Fraud. For reviews, how do you think one could use machine learning? Amazon, we get a ton of product reviews, right? What would be one application of machine learning for product reviews? Huh? Okay, sentiment analysis. You can give him the pink shirt. So you kind of get to know whether people are positive about a product or not. So we do use, by the way, we do run machine learning algorithms on reviews too. Okay, well, okay. Okay. Right. I'm looking for one specific thing. Sentiment analysis is one thing, but what about what are the other things? No, I'm not talking about how you use reviews. I'm talking about how can I use machine learning to make the reviews better? Yeah. I can't hear. Why don't you? Yeah. Fake reviews, exactly. Okay. So detecting fake reviews is again another area where we use machine learning, try and figure out, I mean, there's a lot of reviews out there that are, we actually have sellers who list a product and then from the same machine, from the same IP address, they type in all the reviews saying how great the product is. So that's how we actually detect a lot of fake reviews on, and so on. And again, with text, book search, recognizing entities in a book, and so on. So there's a bunch of different places we use machine learning. And just real quick, I'll conclude with, on forecasting, again, we're looking to predict the demand. And one of the biggest challenges here is there's lots of new products that are constantly being launched. So you don't have much of historical data. So then you've got to use other features of the product to predict the demand. So for a new product, what would be features I could use to make predictions about the demand for the product? Price. Okay, yeah, price may be a good, yeah. Similar products. Who said similar products? A lot of people said that. Okay. How? The vendor. Well, okay. Well, I'm not sure about that. Okay. Well, why don't we give, who said similar products? We can give, okay. You've already got one though. Okay. You're not allowed to answer. It seems like you already know. What's that? Similar products. Okay. Why don't we give him one? We have one final card. Yeah. So yeah, I mean, you can use title, description, category of the product, price of the product. So many of these things can be used to try and predict the demand, right? And another problem is also seasonality. So product demand is a constant, not at every time. I mean, clearly, I mean, a lot of sales happen around Christmas time or Thanksgiving and so on for a company like Amazon. Recommendations. Now, this is one of the problems that actually Amazon was a pioneer on. I mean, we were amongst the first companies to provide online recommendations to customers. And the idea here again is to, recommend to people products that they may be very inclined to buy, right? Again, this is based on past purchase patterns of customers and so on. Search. In search, a lot of machine learning is really involved around understanding the query also, right? I mean, Jaguar is a very famous example. It could mean many different things. So based on the context, Jaguar could be an animal, Jaguar could be the car, Jaguar is some football team in the US. So people may be querying for many different things. So understanding what the customer intent is again very important, and machine learning is useful out there. I'll just conclude with one last slide, and just building machine learning models again is an iterative process. I'm done. This is my last slide. So you start off with your business problem. You typically map your business problem into a machine learning problem, and we did that here in the talk. We took spam detection was the business problem. We mapped it to a machine learning problem, which was a classification problem, binary classification with features that were the keywords, sender, and blah, 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 and then the target was the spam or not spam. You have to collect training data. So for spam, you have to look at maybe your users provide that indicator of something being spam or not. So you need high quality training data. You kind of format your data, clean your data, get rid of bad points and so on. You may do some visualization. A lot of times you do feature engineering. Typically that's like, either you bin your numeric attribute or you sort of prune away stop words, very infrequent words. You may also do some aggregations and so on. And of course, you train your models. Most machine learning algorithms have a couple of parameters that you may have to tune. You try kind of tune the parameters to get the best performance, typically using cross-validation. And if your model sort of meets your performance metrics, so like I think there was a question on how do you know where to set the thresholds and things like that. So you have some performance metrics. You say I want an accuracy of at least 10% of my predictions should be correct, right? I mean, I'm okay with 90% being wrong, but 10% should be correct. So based on that, you kind of see whether you meet those performance metrics. If you do, you deploy the model in production. Otherwise, you have to go back, look for more features, look for more data sources that have predictive power. In the end, you need good features that have predictive power to build good machine learning models. And for a spam application, clearly sender is predictive power. Keywords have predictive power. We all know that there are certain kinds of words that tend to occur in spam emails. So if we have all that, the right set of features, then we can build the right set of models. So with that, I'm just going to conclude, and thanks a lot. You've been a great audience.